Okay, so let's go over non-renewable energy. So when you're done with this lesson, you should be able to differentiate between non-renewable and renewable energy sources. We're going to go over fossil fuels and nuclear, and also to go over the processes of combustion and fission. All right, so first of all, what is a non-renewable energy source or a non-renewable fuel? It's often defined as not renewable on a human timescale. So this can get a little bit fuzzy, but the premise here is that if you think about it, if you have an energy source that is going to take so long to regenerate itself that effectively once you use it, it's used up, at least in your lifetime, we consider that non-renewable. So it is a little bit fuzzy, but um, things like coal and oil and natural gas, of course, they take millions of years to form, so they're certainly non-renewable. But you have things like trees, which are considered renewable. Now, a tree obviously doesn't regrow itself immediately like sunlight comes back immediately or like wind comes back immediately, but a tree does regrow over a short enough period of time, at least most trees, that they are considered renewable. You can think of things like, we get ethanol from corn. Corn will take a few months to grow, you get it back. So even though you can use it, and you can use it too quickly, but it will regenerate itself on a relatively short time scale. So that's renewable. So non-renewable means it's not renewing itself quickly enough for it to effectively be a renewable energy source. Okay. The main non-renewable sources of energy that we use are called fossil fuels. Now, a fossil fuel is a fossilized hydrocarbon derived through natural processes from organic material. We're going to go over this process here in a minute or two, but these are fossilized, so that means they are old. They are basically they become they've turned from one thing and they've been metamorphosized into something else. Okay, so they're ancient. They're hydrocarbons, and hydrocarbon actually means they're derived primarily of hydrogen and carbon. Okay, they're derived through natural processes. So these form naturally, despite some of the stranger corners of the internet that tell you that these are, man-made. They are derived from natural processes, and they are derived from organic material. We'll go over that in a minute. So these are all carbon-based, carbon and hydrogen-based, formerly living things. Okay. Our main three fossil fuels: coal, oil, natural gas. Okay. I'm sure you're familiar with those. Now, nuclear is not a fossil fuel. Okay, this is really important. Nuclear is not a fossil fuel. And it does not, because it's not a hydrocarbon, it's not derived through a natural process from organic material, and it's not fossilized actually. So the nuclear fuel that we use came actually from, it's extraterrestrial, it came from, old supernova. So anyway, the point is these fossil fuels are non-renewable, but nuclear is the other non-renewable. So those are our four non-renewable energy sources, okay? So what is a renewable energy source? Well, it is renewable on a human timescale, okay? So, pretty easy to remember. If you remember one, you can remember the other. There are a lot of examples of this. Solar, we'll go over these throughout the semester, so I'm not going to focus on these, but like solar and wind and biomass, biomass is any, biologic organism, um, or any material from a living or recently living organism. Anyway, they're renewable on a human timescale. Solar, obviously, you can use it and it's just going to come back, if nothing else, the next day. Wind is the same way, and then trees and other forms of biomass, they do grow back. Okay, so they're renewable on a human timescale. They functionally, even though you can use like a tree, you can cut down trees too quickly. If you do it right, they are renewable. Okay. There's also a few others that we'll go over: geothermal, hydroelectric, wave, and tidal. We'll get to more of those throughout the semester. Okay, another concept I want to go over is carbon-free. So one of the main premises of this class is to, investigate alternative energy sources. Alternative energy, effectively, we're alternatives to fossil fuels, but also nuclear. Nuclear is a little bit of a gray area, but carbon-free is an important term that we'll go over throughout the semester. But carbon-free specifically means that there's no carbon emitted. Okay, And I'll go over the carbon, the carbon emitting process here in a minute. So when there's, use these energy sources, solar and wind, there's no carbon dioxide emitted at all. There's nothing emitted, as a matter of fact. Whereas something that's carbon neutral, which is a subtle but somewhat important difference, carbon neutral source means there's no overall carbon emitted. Okay, so you think about it, if you take biomass, so think about a fire, right? So you burn wood, you actually emit carbon dioxide. Okay, you emit smoke, you emit some other stuff. But it's carbon neutral because with a tree or any other form of biomass requires carbon dioxide to grow, right? If you're familiar with photosynthesis, a tree is going to pull in carbon dioxide when it grows, and when you burn it, you're just emitting that back out. So if you think about the two sides of that equation, the carbon input and the carbon output, it's going to balance by definition. It has to balance because you can't, get any more carbon than you had initially put into the biomass. So the point is that carbon neutral sources, they do emit carbon dioxide, but they don't emit any more than they took in when they were growing. So it's a subtle but I think somewhat important difference. When you look at carbon accounting, they generally just consider carbon neutral sources the same as carbon free, but I wanted to point out that there is a difference. Okay, so that's basic renewables and non-renewables. So a really interesting thing is how were fossil fuels formed. So first of all, petroleum, or oil and natural gas, are formed effectively the same way. And basically you have living organisms. Remember, these are hydrocarbons, so they're derived from organic material. So coal or natural gas and oil both start out as living organisms. To be fair, this illustration is not the best because most of oil and natural gas are not like, giant black squid and, whatever kind of rays and giant worms these are. More often than not, it's microscopic organisms like plankton, phytoplankton. But anyway, they are formerly living organisms that die, okay, and they sink to the bottom of the ocean. They get covered. Okay, so here's your thick layer of organic material. They get covered by hundreds or thousands of feet of debris from erosion, and then over the course of millions of years, those, you notice here, the animal and plant remains, they actually are converted into oil and gas. Okay, and then that's, these deposits are what we that's the oil and gas that we mine out of the ground. And interestingly, the oil and gas, it's not like there's a big pool of oil and gas down here. They actually exist in the pores of rocks. So if you saw a rock that had oil deposits in it, you probably wouldn't even know it because you can't even see the oil in there. Anyway, that's where the oil and natural gas comes from. If you think about the thermodynamics of the whole process, remember all these organisms, they get all of their energy from the sun, whether they are a plant or they, all animals get their energy ultimately by eating plants or eating an animal that ate plants. So all this energy comes from the sun. So effectively, this oil and natural gas is energy from ancient sunlight. Pretty interesting. Okay, so that's oil and natural gas. Coal is formed in a very similar process, but coal is actually not the remains of old plants and animals. It's actually just the remains of old plants, and these were formed if you have a swampy area with a lot of biomass in it. These living things, they die, they sink to the bottom. If you've ever walked in a swamp, if you're familiar with it, you have that like sort of thick mucky stuff at the bottom. That's all this organic material that eventually it settles in, and eventually it turns into peat. And then if it gets buried under sediment, and then over millions of years, the peat then gets converted into coal. And there are actually different grades of coal. The lighter coal is lignite coal, and then you get the darker stuff like the anthracite. Okay, so these are ancient dead plants, no animals, whereas oil and natural gas are plants and animals, but they're primarily plants as well. You almost always find oil and natural gas together. That's why they're lumped together. Okay, now uranium is totally different. Um, it came from, it's extraterrestrial, came from stars. So it's, there for billions of years. And this is what, this is a uranium ore. Okay, so you extract these out of the ground, and then what you do is you sort of, you process it, so you end up with this stuff called yellow cake, which you may have heard of before. Okay, so this is what uranium yellow cake looks like. Now there's a refining process from there, but the main point here is it's non-renewable, and it doesn't come from organic material like coal, oil, and natural gas. Okay, so how do we get the energy out of these sources? And this is an important distinction, because this plays a large role in the sort of sustainability aspects, especially with regards to climate change, of different energy sources. Okay, so with coal, oil, and natural gas, you probably know if in order to extract the energy out of that, we just burn it, right? So what about nuclear? Do we burn uranium to get the energy out? I mean, is that what we do? As it turns out, we don't do that. Okay, so I'll get to that in a minute, but this process that we use to extract the energy out of coal, oil, and natural gas is called combustion. I'm sure you've heard of it. So the basic combustion equation is fuel, oxygen, and heat, and then usually some impurities. And then you're basically oxidizing this fuel source, and you end up with the primary byproducts are carbon dioxide, water vapor, and heat. Okay, so the beauty of this exothermic reaction is that you generate heat, and then this heat goes back and feeds this part of the reaction. So that's why it can just burn and burn and burn. As long as you have, those three things, the fuel, oxygen, heat, you can continue to burn. Now, in this equation, of course, the coal, oil, and natural gas is your fuel source. And again, as long as you have fuel, oxygen, and heat, you're good to go. Now remember that these are hydrocarbons, so these are primarily carbon and hydrogen. So think about it. You have a bunch of carbon and hydrogen, you add some oxygen, and you get this carbon dioxide, water vapor, and heat. Okay, so there's your carbon, there's your hydrogen. The one thing I want to point out in this equation, this carbon dioxide is a really important aspect of it. This is one of the main reasons why we're concerned about fossil fuel use, because you cannot get around the fact that this emits carbon dioxide. Okay, now there are things you can do with the carbon dioxide to mitigate the process, but there's really nothing you can do about that. Okay, so let's get into, so we actually don't combust uranium. What we do is we use fission. So how does fission work? Fission is pretty straightforward, and conceptually anyway. You fire a neutron at this uranium atom. It basically splits. Okay, so when you split the uranium, what it does is that it actually releases these neutrons, and it releases energy. Okay, so this whole splitting, that's the fission process. Okay, so what's really interesting about this, and why nuclear energy is so useful and dangerous, as a matter of fact, is that you split one of these, okay, and then it's going to release more neutrons, and guess what? If the material is enriched enough, then these neutrons are going to hit more uranium atoms, and they're going to split those, and then they're going to release more neutrons, and so on. So it's a chain reaction. You've probably heard that term. So the byproducts of fission are the neutrons, but really importantly, it's releasing heat energy. So when you have a nuclear fired power plant, you're not burning the nuclear material, you're not burning the uranium, you're splitting the uranium atoms, and they're releasing energy as they undergo fission. So that's how you generate, you basically extract the energy out of nuclear material. Okay, and that's it for this presentation.